to the station, to the fjord. It's a coastal station, and well, that's definitely like a good spot for snow research. We got quite plenty of snow in terms of like surroundings, as it's like high Arctic setting. And like a bit about infrastructure itself. So it's a manned station with 8 to 9 overwintering personnel. So we're in, it started in 1957 with geophysical year. Then station was seasonal, and since 1979 we're full steam operation. There's around 22 places for scientists. Well, it's said it's from March to October, because it's possible to get there between March and October. Well, if you have a project for winter months, then it's also possible to stay at the station. But in station history, we had people doing that just twice. We ran WMO station. We got 2 wet labs, ion chromatography lab on site. There's a permanent GPS station, which might be crucial for some of the researchers. And it's nothing new since this year. Was we all have Starlinks all over the world, but it was a big thing 2-3 years ago, as we had internet access. If you want to go to Hornsund, we are open for projects, and application deadline for the station is February. And well, you got to like really be fast, as there's not much space for researchers all over the year. But getting to monitoring, as I said, like Hornsund station is a coastal station. It's around 10 meters above sea level on a coastal plain. And for snow, we have 3 main areas. So our main monitoring site is Fuglebecken catchment. It's like close to the station, the closest catchment. And we also do snow measurements on Hansbren. This is like a mid-size tidewater glacier, and on tiny Bren glacier in Aredalen catchment. This is like small glacier, which is super fast melting out. Okay, so for Hansbren, this is it's about now 14 kilometers long tidewater glacier, and we have a network of ablation stakes. So like snow measurements are directly related to mass balance measurements. For pretty long time, as for 12 years, we used to have like land surveyor in Hornsund, and we did regular measurements of snow depth and ice melt. But since 2019, due to high crevasse risk, we switched to classic twice-a-year measurements. So we have only maximum accumulation snow depths on the stakes, and it's basically done for mass balance. And in springtime, we do snow pits, like 3 snow pits in accumulation area at ELA and at the bottom of the glacier, mostly for SWE, snow stratigraphy, and snow chemistry, as we do quite a lot of snow chemistry in the area. The other glacier we work, it's called Arebren, and now it's less than 2 kilometers size. And there we do a bit more, as it's safer. So we do surface mass balance, but we measure stakes more often, around once a month. Then we do snow pits once a year, and we do fresh snow sampling after every major snowfall. There's fresh snow sampling for chemistry. But then next to the station, we ran Met Station, and there we have a record of snow depth and SWE. And for SWE, that's the longest record for Svalbard, as We started in 1983. There's some gaps, but it's like every 5 days we get manual measurements of snow water equivalent in a site next to the Hornsund station. It's not the best place. Well, it was set up like this in the 80s, and we continue in this place. It's not the best place in terms of representativity. And because of that, we started in 2014, we started measurements, snow depth and SWE measurements in the Fuglebecken catchment. It's like catchment nearby, like half an hour walk to the catchment. And we do weekly measurements in 20 points for snow depth and SWE. And there's also snow sampling. Due to avalanche safety, it's done only in the flat area, so between 0 and 50 meters above sea level. Then when it gets steep, well, we don't want people to work on slopes too much, mainly due to avalanche danger. What else? In a Fuglebecken catchment, we also do snow distribution with time-lapse cameras. We used to have for 6 years camera installed on mountaintop, but then we had quite a lot of issues, and now we use only time-lapse cameras installed in the coastal zone, also looking at the slopes. But this was used for like snow distribution maps and snow extent graphs for the area. We also do, as I said, we also do precipitation monitoring. So in a Fuglebecken catchment, we got event-based precipitation monitoring and sampling. So anytime there's rainfall or snowfall, it's collected and then it's monitored, and then it's samples are measured directly at the station. Then we also do this fresh snowfall sampling in Armin, and it's in elevation profile. And we do every year snow pits at both glaciers. And this is mainly for major ions, heavy metals, and for past 2 years, we had a project for black carbon. And we'll see how it continues. It depends on funding if we'll continue with black carbon, as there's need for funding for sample analysis, as we do not do that on site. So I told you about the lab. So we got 2 clean labs. Well, wet labs. One of them is it's not super clean lab, it's like cleaning standards of major ions and heavy metals. So we do basic conductivity, pH, major ions composition, bicarbonate, and we process samples for heavy metals, but then they are measured in external lab in Poland. And well, our main efforts in terms of snow monitoring and running projects are based in Fuglebecken catchment, as it's like close to the station. So also in terms of logistics, it's possible to work there. And we got regular measurements of snow depths, and snow distribution monitoring. There's also fresh snowfall and precipitation sampling. During the summertime, we run hydrological monitoring. There's kind of like a gap between snow monitoring and then hydrological monitoring, as during the melt period, when everything is still a bit frozen, we have problems with measuring runoff. In the catchment, we also have like free boreholes for permafrost monitoring. So there's information on that. It's close to this WMO meteorological station, so meteorological data are also accessible. And it's possible to get like remote access sampling and equipment maintenance if you would like to run a project with us. What is a big thing, we have access to electricity and internet right in the middle of the catchment, and we try to keep it, it's complicated, but we try to keep it like as snow scooters free zone, at least the area where we do fresh snow and precipitation sampling. Well, as most of you, we have a lot of issues with equipment. One of the biggest issues, especially in higher elevation, is icing. That's one of our time-lapse cameras. And the other thing is polar bears and reindeers, as a lot of equipment that is installed in a field ends up on tundra because of reindeers and polar bears. So those are like big issues and challenges we have in a field. And well, we try to work on harmonization of measurements. So now, especially with measurements on glaciers, we try to get along with the protocols we publish together within the science community. We also try to keep like same standards for snow pits. So there's some efforts on that. Those efforts are heavily backed up by the science community, which is like Svalbard Integrated Arctic Earth Observing System. That's like umbrella organization for research infrastructures in Svalbard. And within this community, we try to harmonize our measurements. And well, what's new and what are our plans? Well, new things we did this year in Hornsund. At the beginning of this year, we started with Cryos project. That's infrastructure project from Norwegian funds, and it's aimed to like cryosphere integrated observation network on Svalbard. And within that, in Hornsund, we got 5 new snow stations installed. Those are like SPICE sensors for A2PS. And we installed them in elevation profile in Fuglebecken catchment. So now we have 5. Actually, I installed them 3 weeks ago in September. And hopefully they will survive the winter. They are all connected via LoRaWAN protocol, so we have live access to data. Then in the summertime, we installed new GNSS antenna for GNSS IR snow depth and hopefully SWE assessment. And we bought new liquid water content sensor. That's a manual one, so we will use it mostly in spring for liquid water content measurements. And this is all to unify infrastructure between the main research infrastructures in Svalbard. So all over Svalbard at the regional stations from universities and also in Alesund and Longyearbyen, we plan to have similar infrastructure for snow depth, SWE, and meteorological parameters measurements. And this spring, we start together with colleagues from Norway, also from UNIS and NOR's GPR measurements campaign, mostly in big valleys and on slopes. And those GPR profiles will be used for calibration of ISAT2. And last thing, we are still waiting for like 100% confirmation of funding. But if it works, then in May next year, we will run in Hornsund big campaign during the melt period, as we know quite some stuff about snow during the dry season and maximum accumulation. And we have almost no information in wet season because like people don't want to go and dig in a slushy snow. And we plan 4 weeks campaign in the Fuglebecken catchment, which would be closely connected to with chemistry and microbiology. So it's going to be like mix of snow hydrology, snow physics, chemistry and microbiology. And yeah, oh, I'm missing one slide. It's quite easy to get to Hornsund in terms of funding, as we are Interact station. So you can apply within the Interact call. The other way to get funding to get to Hornsund is you can try with SIOS, as every year SIOS has access call for access to research infrastructure in Svalbard. And we are part of SIOS, so you can apply for money to come visit us. And Research Council of Norway is also funding, it's called Arctic Field Grant. And those are grants aimed at young researchers, basically. So if you have master or PhD students that would like to do some field work in Hornsund, then you're more than welcome. Okay, and that's all. If you have any questions, then yeah, I'm here.
Great, thank you. Just to sort of keep things moving, because we have 4 sites, if you have questions, feel free to put them in the chat, or if we have time at the end, you could ask any of the speakers at the end. So thank you, that was great. And we'll move on to Simon Filhol next for Norway.
Hey, hi everyone. I'm trying to see. Come on, here we go. No, my bad. Now, so hi everyone. You see the slide well?
Yes, looks good.
Okay, good. My name is Simon Filhol. I'm a researcher at the University of Oslo. I've been here for some years, and as I arrived, I went straight to work in Finse. And Finse is a research station, so there is no monitoring except one part that is by the Meteorological Norwegian Institute. So we don't have really long-term programs that like Bartek could present, but I'll present the sites in terms of snow and what data is available, and hopefully you'll enjoy. So Finse is located at 60° north. It's in the southern part of Norway, and it's located like halfway between Oslo and Bergen along the train line. And the train gonna become important as there are no roads that leads to Finse. It's also very close to the water divide. So in Norway, we have a very strong influence from the west, with storms coming from the west, hitting the mountain range and then going towards the east. So this is the big picture. When we zoom in, there is on the south, we have Hardangerkullen, which is an ice cap. It goes up to 1,800 meters. I think this elevation is pretty old, and it's retreating. It's melting quite fast. And in the north, we have a mountain range, and Finse is itself located at 1,200 meters. It's quite flat area. It's part of a big plateau, and it's covered in tundra. So this is how it looks like right above the building of the research station. It's a lot of water and a lot of rocks. It's deglaciated landscape with pockets of till in between bedrock, and with a river that is fairly big. And you see here the glacier's outlet from the ice cap. And this picture was taken in end of May, so you can see the drifts that are left in the landscape. This is a video to show you the surroundings. So here you see the building of the research station itself, which was built in the 70s by ecologists. And a new building was built to receive courses and seminars that you see now. And this video was taken in late April during a breakup and I chose this time because you can see like how places are bare of snow and other places have a lot of snow accumulation, a lot of drifts. So the wind plays a huge role in snow distribution in this area. And it's relatively flat, but it has quite developed microtopography, which are microtopography. It's not micro, but it's neither like large mountains, but it's plenty to capture a lot of snow during the winter. So in terms of climate, in summers it goes up to 15 maximums around now in the 20s. In the last few summers. In the winter, it can get minus 25, minus 30, and but with a regular melt event coming through the winter. We're very close to the ocean, and so we're very influenced by the ocean weather. In terms of precipitation, most of precipitation comes in the summer month or in the fall, and it's about between 1,000 to 2,000 millimeter per year. It's measurements, direct measurements from precipitation gauge, which is not very useful there as there's a lot of wind, and the wind is very often above 6 meters per second. So drifting snow drift is prevalent in the landscape. And even in summer, it's blowing a lot. And I've been there in 30 meters per second wind. And the reason for that is we have in the south, we have the ice cap, and in the north, we have this mountain range. And so the air is funneled into this valley, and the winds can get really, really strong. So as a matter of fact, we have a very bimodal type of wind rose. And yeah, so it's kind of a natural wind tunnel. In terms of climate evolution, the warming trend is mostly significant, or is significant for every season except winter, and those are from the observation. So the winters haven't changed so much since the 70s in terms of, but the other seasons are changing in terms of temperature. The snowpack we have, it's maritime snowpack, so a lot of it falls in and then is reworked by the wind and accumulates after in layers that are going through some various melt events, especially when the winters are dominated by storms coming from the west. And when the accumulation and the dominant wind for the season is from the east, we have colder weather and less melt forms. But this is kind of last year, some students that were with me dig out like ice layers in the snowpack. It can be built as a really nice structure. So it's quite influenced by the rain. In terms of measurements, or snow measurements and hydrology, we started here in 2012 to measure snow distribution on a 1 by 1 square kilometer grid here with GPS, GPR, and later with drone. The premise of this work was to look at ground surface temperature under the snow. And then there was a weather station by the Meteorological Institute that was installed here, and we, under an initiative of the university, we bought a lot of sensors and equipped the weather station with additional sensors I'll show after. And then we've established 2 watersheds where we measured discharge, one in the north that is mostly non-glaciated, and one in the south that is glaciated. And the one in the north is abandoned because we don't have the manpower to maintain it. And the one in south now has been taken over by the Norwegian institution to the NVE, so Norwegian Water and Energy Directorate, that is responsible now to measure discharge and run the discharge measurement. So the weather station, now we have a really nice set with the classical Norwegian weather station with 10-meter wind speed, the 10-meter air temperature and humidity, 2-meter air temperature and humidity. Those data are part of the WMO network. And then on top of that, we added a 3D sonic anemometer along to like CO2 and water vapor gas concentration sensor to do some ecovariance measurements. Then we have long wave and shortwave incoming and outgoing radiation. We have a distrometer. We have flow caps to measure the wind transport at the station. And the soil is equipped with soil heat flux sensors and moisture sensors. There is a skin surface temperature sensors, snow depth. And lately, a bit more exciting, I think, is the time-lapse LiDAR that we've set up at the top here of the mast. And we can observe continuously the snow accumulating around the weather station. So most of the sensors were added in 2016 and have been running since, with some gaps with power outages. But now it's a mostly complete data set. In terms of snow distribution, I mentioned the 1 by 1 square kilometer grid. So this is run when I before and when I arrived, systematically every winter with a GPS line that we pull in on the sled and measure then differentiate the elevation to get snow depth. And when we could, we also do some drone measurements that now we try to do once a year when we have manpower. So it's there's no money for monitoring, so it depends on the research project and the manpower available for going to do the measurements. But there's a record that exists and is available. We also use it. We have many people working with remote sensing here. So it's also a test ground for doing remote sensing. It's often cloudy. So, but still, we have days where we can get the satellites can get through. And here's an example of the work by Gillies, where she's reconstructed snow cover duration from MODIS, Landsat, and Sentinel-2. This is a work in progress. But before being a site for measuring snow, it's a site that was developed by ecologists, and there's been a lot of studies on ecology. It's one of the longest record on lemming population. It started in the 70s and has been run through until now. The record that is older started in 1930, but so it's a big ecological site. And here on the left. On the right, sorry, it's all the studies that have been, it's a review of all the studies, ecological studies in terms of plants, fungi, animal, which are like rodents and invertebrates. So there's quite a lot of knowledge about the place. And it's part of the ITEX site as well. So in terms of practicalities, it's a place where courses and seminars can be organized. There's a nice building for that. It's a place to reach by train, not by car. The train can be taken either in Oslo, downtown Oslo. It's 4.5 hours to get there, or from Bergen. Then the station is 2.5 kilometers from the train station. And on site, it's either on foot. There's one snowmobile that is in poor condition, but still running, and then skiing. Many people here ski. It's a big place for Norwegians to go ski also, and kite surfing. Then there is the station itself has 42 beds with 15 bedrooms. There's one lecture room and there's some lab space, but It's quite old, but there's a lot of space. The buildings are big, and there's a small workshop, so there's a lot of space to work. And finally, if you want to come to the research station, it's for funding. It's part of the Interact network, and I think it's one of the easiest way to get funding to come here. And there's a website run by the biology department who is responsible for the research station, and you can find all the information you want you will need. And the two contact person outside of us doing snow and geophysical observations there are Torbjørn Ergon, who's professor in biology. He's responsible for this. He's director of the place. And then the person running the place is Jens, and he is the one to ask any questions, practical questions, and booking and all of that. So with that, we welcome you to come to Finse. It's a wonderful laboratory for blowing snow, and the more, the better. So thank you very much.
Great, thank you. Okay, I think, again, if you want to save questions for the end, we can ask of all the speakers at the end. And then next, we're going to move to Antarctica. Armin, you're ready to share?
Yes, hello. Can you hear me well?
I can hear you, yes.
Nice. I'm going to share. Can you already see it?
Yes, I can see the slides. They're not yet in.
Okay, I go to presentation mode. Okay, great.
Great.
Yes, so in the next minutes, I'd like to take you to Antarctica and talk about why I went to Princess Elisabeth Station to measure snow transport and sublimation. I've been doing my PhD at the Swiss Federal Institute of Technology in Switzerland, and it was under supervision of Michael Lehning. And we have a project where we go to Princess Elisabeth Station since 2016-17. And I will tell you everything in a couple of minutes. So I'd like to start with a picture when you're at the station. Sorry. Okay. And you look out of the window, it can look like this. And if the wind is really strong, then it can also look like this, because the snow particles in the atmosphere reduce the visibility very much. Yeah, this is what we are mostly interested in, the snow transport and sublimation. And I will first start with introducing the location and conditions at Princess Elisabeth Antarctica Station, or shortly PEA Station. Then talk about the facilities that you have there if you want to go. And then come to our project, the goals and the methods we use and challenges we face. Okay. So Princess Elisabeth Station is a Belgian research station. It's managed by the International Polar Foundation, and it's located in East Antarctica at an elevation of approximately 1,400 meters. The distance to the coast is almost around 200 kilometers. So unfortunately, I couldn't see penguins there. They live closer at the coast. If you go there, it's typically accessed by airplane from South Africa. And each year there's a Belgian Antarctic expedition. And so they only go to the station in austral summer. So it's only occupied from November to February, and not in the austral winter. there is space for approximately 25 to 40 people, and the air temperatures in the surrounding can be quite comfortable in summer, at least. On warm days, you can have -5 degrees Celsius, but in Austral winter, it would go down to -40 in cold conditions. If we zoom in a bit, we see there is a mountain range close to the station. And this mountain range also shelters the station a bit from the strong winds that you can have frequently in Antarctica, mostly from easterly directions. And we have mainly two sites where we measure the snow transport. One is directly at Princess Elisabeth Station, and a second one is on the other side of the mountain range, where the Antarctic plateau begins, and where also elevation is about 1,000 meters higher. So the conditions are quite different. Okay. Yeah, I'd like to introduce the facilities. So you have the main building highlighted here, where you have living and office spaces and bedrooms. And they call it a zero emission station because the energy is taken from solar and the wind energy. The only exception are the vehicles, which are usually, as usual, powered with fuel. And yes, so people there are often, it's a mix of technicians, engineers who maintain the station, and scientists, and everyone is welcome. You need some funding, of course, to go there. But the atmosphere is very, very friendly. We had very comfortable rooms there, and languages spoken are mainly French and English. French, at least the technicians and engineers, but there are also many of them that speak English. And if you interact with them, you need support, they are happy to help. For example, we have automatic weather stations, and I needed a battery, and they had them available at the station and helped me out to connect them with a solar panel and so on. Here you have this part of the building with mechanical and electrical workshops. I had some space there to prepare my instruments for the field, which was useful. You also have bedrooms in the upper part of this building, of this part, where I was located. And so there are also these scientific shelters, because the station is anchored on rocks on a small ridge, and to both sides of the station you have these shelters where scientists can install instruments or equipment for direct use. You also have mobile science containers, so that's interesting if you want to go on a traverse for longer time and travel for longer distance over the ice sheet. They can carry these containers as a mobile laboratory, and then they are partly also used, if not needed for traverses, to store equipment from one year to the next. There's also the option to install instruments on the roof, at least for atmospheric measurements. That can be interesting. And other projects do that. They have a broadband internet connection, which is very useful if you want to transfer data remotely. And then what we used very much are vehicles to reach our field sites. So myself, I traveled with these ski-doos also to the second site on the other side of the mountain range. At that time, our automatic weather station that you see on the right here was already installed there, and for maintenance we could go there fastest by skidoo and carry some material on sledges. And then my colleague who was there a year before to install the station used then this car with field guides and set up everything. Okay, now about our project. You see here a picture of one of our automatic weather stations. And in Antarctica, you have commonly strong winds, especially in the escarpment zone and during austral winter, when the katabatic winds are very persistent. And that means also there's a lot of snow transport, and you can imagine that this snow transport leads to very efficient sublimation of the snow particles. And it's still very uncertain how much of the snow sublimates in these conditions, and that's where we want to find out more. We aim to measure automatically throughout the year to cover a variety of conditions for the weather and in different seasons. And we want to know the horizontal flux of snow transport, also the turbulent fluxes of vapor and heat. So for the vapor, this flux corresponds to sublimation. And then we have standard meteorological sensors, which are very useful for interpretation, and also the snow height changes. Then if we go there and maintain the stations in summer, we perform complementary measurements, for example, snow hardness profiles with a snow micropenetrometer. And we also used photogrammetry with a drone to survey the surface structure over a larger area and better understand patterns of erosion and deposition that can be associated with the snow transport events. Finally, we want to use this measurement data to improve our process understanding of snow transport and its contribution to sublimation. We do that by combining measurements and small-scale models to get a more complete picture. And then we also use the measurements to validate and improve our models, including large-scale models that can be applied to the whole Antarctic ice sheet to determine surface mass balance. And this is a very important quantity in the context of sea level rise. Okay, how does the station look like? I want to talk a bit more about these automatic measurement stations. We have two very similar ones installed since 2016-17. And on the right side, you see the station on the second side, which we had there for 3 years. Currently, it's not there anymore because of some issues that I will explain later. And these sensors we use, you have already seen in the talk before, the flow cap sensor for measuring horizontal snow mass flux. We also have snow particle counters, which measure accurately at a specific height the number flux of particles and the size distribution, and can also derive a mass flux. We have then also for the turbulence measurements edicovariance to measure the fluxes of latent and sensible heat. We can also use the Molino-Bukov bulk approach with standard meteorological sensors. But for our main focus of transport, snow transport events, this method has some issues and it's not very accurate. So we focus a bit more on the eddy covariance. Then we have other standard meteorological sensors. Here is sensor for global radiation. And we also have since 2 years at this side on the left measurement of all 4 radiation components. Then for the snow height, we have this sonic ranging sensor. And now about the challenges. First of all, we wanted year-round measurements, but this is very tricky, especially because the station is only occupied in summer. So there's a long winter season and there's nobody there to maintain or check if everything is working. So we often had the problem that there was a problem with the power supply in austral winter. The stations are designed to be autonomous with a solar panel and a small wind turbine, as you see on the right side. But the wind turbine, after 2 years, didn't work properly anymore. And also in austral winter, you don't have solar radiation much. And so there was not enough power. And we had big data gaps in winter. We solved that, at least for the station that you see on the left, by moving it into the immediate vicinity of the PEA station. So we could connect it to the PEA electricity. And at least for the last 2 years, we have not the problem of winter gaps for this site. There were other problems. So in the end, we didn't get, let's say, a full year of all sensors working completely. But maybe this year, and we are at least, we still have a valuable data set with a lot of things to still investigate. Then the other issue, the other big issue is snow accumulation, because these areas experience net accumulation. Sometimes when I was there, it was approximately half a meter compared to the previous summer season of snow accumulation. In the case of this relatively new site here on the left side, where we are directly at PEA station, we don't have this problem anymore, because this location is quite unique in the sense that we are close to a reach where the wind apparently hinders the snow from accumulating too much. So there we didn't have the need to move the station higher every year. But for the other site, it looked like this in the last season. And we decided in this case to remove the station, because it's a lot of effort to dig it out in that remote place. And we had other issues with the power supply. And so there we still have some data for a month until March, for example. But then there are unfortunately big data gaps also in austral winter. Yes, so if you're interested in going there, it's a very nice site. Also, our data is partly published. So far, only a small part, but there's probably more in the future. And you can also contact us already now if you want to use some of it. And for going to Princess Elisabeth Station, it's best to directly contact the International Polar Foundation. You will find everything on their website. And thank you very much for your attention.
Great, thank you. We're running out of time, so we're going to move directly to Andrew. Maybe we're a little ambitious trying to fit 4 talks into an hour, but hopefully people can stick around to hear more about Reynolds Creek. And then again, we might not have time for questions afterwards, so feel free to use the chat for the speakers so far. Go for it, Andrew.
Hi, everyone. Thank you, Sinter, for hosting these quarterly talks. My name is Andrew Hedrick. I'm a research hydrologist in Boise, Idaho at the Northwest Watershed Research Center. I'm one of a few scientists that sort of operate the Reynolds Creek Experimental Watershed. And it's We have some primary collaborative universities listed here at the bottom, between Boise State, Idaho State University, University of Idaho, University of Texas at El Paso, and University of Wyoming. It's kind of a theme, I guess, today that we have some windy sites. So our site is our watershed is probably the least windy of what's been presented. Sorry, my computer is having some issues. There we go. Some background for Reynolds Creek. It's located in southwest Idaho here in this map of the U.S. on the left. It was established in 1960 by an act of the U.S. Congress to conduct long-term research in water supply, seasonal snow, soil freezing, carbon cycling, water quality, and rangeland hydrology. Just dive right into the measurement infrastructure. This is the watershed on the left. It's a 238 square kilometer watershed, but most of the snow centric research happens in this about 55 square kilometer portion to the south, in the green. Some of the different measurements that we've been taking since 1960 or the mid 60s are stream flow. This is an image of the Colgate Weir, which is sort of the outlet of the snow dominated area of the basin. As you can see, it's largely over engineered, but it's come in handy a few times with some flood events that have come through. We have 11 of these weirs. One stream flow site is actually a flume, but the other 10 are weirs, similar to this, just in different sizes depending on the reach. We're measuring precipitation currently at about 23 sites. We use a dual gauge approach. I'll talk about it in a second. At one point we're measuring had one measurement site per square mile in the watershed, and that was a little bit overkill. We have 32 met sites. We're looking at snow properties, of course, at Reynolds Mountain East and the southern tip of the watershed, and we have 4 eddy covariance sites in an elevational transect going up on the eastern side of the watershed. So precipitation, as I mentioned, we were oversampling quite a bit until the early 80s, and then we decided to cut back quite a bit. Now we're measuring at 23 sites, collecting 5-minute data, which is telemetered by radio to our office here in Boise. In the early 70s, one of my predecessors, Russell Hammond, created this dual gauge correction to estimate actual precipitation using a shielded and unshielded measurement and an empirically derived constant that was catered to Reynolds Creek. Climate stations, we're measuring all of the climate variables you would need to run, say, an energy balance snow model, temperature, humidity, wind speed, direction, incoming shortwave radiation. At some of the sites, we're also measuring incoming long wave. We have a couple of 4-component radiometers sprinkled throughout the catchment. We have some 3D sonic anemometers for the eddy covariance sites. Then we also have soil profiles of moisture and temperature, snow depths at the higher elevations, and then we have a snow pillow at Reynolds Mountain East. Diving to Reynolds Mountain East, this is kind of the zoomed in part of the catchment. It's about 4.4 square kilometers. It is a snowdrift dominated site. It has a weir at the outlet, which gives pretty good estimates or measurements of stream flow. And currently we have 2 precipitation sites and several other meteorological sites. And you can see the elevation from 2000 to 2150 meters. So really measurements started in about 1960. This is an image on the left of the weir when it was in the winter after it was installed. The weir house actually burned down earlier this year due to a propane fire, is what we suspect. It burned down when nobody was around, luckily when there was snow on the ground, but it just got recently rebuilt this month. Here's in the middle is the snow pillow site in the late 60s, and on the right is some of the snow pillow development that happened in the late 60s, mid 70s. sort of a timeline here of Reynolds Mountain East. 1959 was when Congress authorized Reynolds Creek as a federal research facility. The first snow course measurements were in 1961, and that goes all the way through the present at Reynolds Mountain East. There's also 7 other snow courses in the upper elevations of the watershed. The weir was installed in 1963. Snow pillow design development studies were carried out in the late 60s through the early 80s. In the late 80s, Reynolds Creek was used as a WMO precipitation measurement intercomparison site. So there were a lot of gauges, different kinds of gauges that were installed at the lower elevations of the watershed, and then, but also some other gauges installed at the upper elevations of Reynolds Mountain East. ISO model was developed and tested by my predecessor, Danny Marks, at Reynolds Mountain East. And then since 2001, we've been carrying out some intensive snow surveys. Those are sort of developed and for a long time managed by Adam Winskill before he moved to Switzerland. And now we're moving towards a UAS TLS snow survey approach. Here's just here's an image of the intensive survey map when we were performing those up to 2018. The idea is to help quantify total basin surface water storage. So we measured snow depths on a 30-meter grid with 10-meter offsets, so about 860 measurements per survey. We were also measuring snow density with a SWE sampler, 20 to 30 points, between 1 and 3 measurements per point. Then we used the density depth relationship during the survey to distribute the densities to the grid. Since 2019, we've continued using the density measurements approach, but we're also now performing our snow depth surveys with UAS. I thought I'd just throw in some images of the SWE maps from 2001 to 2018 for the intensive surveys. So you can kind of see just the drift development in different years. Most years we had 2 surveys, some years we just had 1. And you can really see the kind of the interannual variability in the uniform distribution some years. And just the pillow is plotted, the pillow location is plotted in blue and listed for the date of the survey. Now I'm just going to move to another catchment briefly. This is Johnston Draw. It was also circled in that one of my first slides. It's on the western side of the catchment at Reynolds Creek Experimental Watershed. It's 1.8 square kilometers, ranges about 1,500 to almost 1,900 meters in elevation. The weir it's got a weir down in the eastern portion of the basin, and then an elevational transect of met stations going up and 2 precip gauges. So Johnston Draw is more in the rain snow transition zone, so it's important for semi-arid hydrology. The stream flow in this catchment is heavily influenced by snow drifts, as you can see down the lower image. The weir was installed in 2002, and then for a few years after that, work was done installing the met stations every 50 meters going up the watershed. And the point of that was to quantify how the precip phase changes during storm. And then recently, about 3 weeks ago, we had a prescribed fire. And this is great because it's really bringing in a lot of different institutions to study how hydrological and biogeochemical changes are happening in the watershed post-fire. So I think a lot of really, really cool research is going to come out of that. And then just a couple of previous studies that were done in Johnston Draw. This was performed by my predecessor, Danny Marks. They were looking at precipitation phase during storms along an elevational gradient. On the lower left, you can kind of see where the met stations move up in the watershed. And they were really, it was kind of neat that they were able to show how these sites change from snow to rain in the period of a couple of hours for a few different storms. And they also determined that, looked at phase partitioning using air temperature viewpoint and wet bulb temperatures, and found that wet bulb is the best method for phase partitioning in Reynolds Creek. Trying to move along here. And then lastly, the recently Leone Hewitt, who was a postdoc, had a study looking at how surface water input compared to measured stream flow in 4 different years. So there was a primarily rainy year in 2005, a snow year in 2010, a high precipitation year in 2011, and a dry year in 2014. And we used the ice snow model that was informed with precipitation rescaling from a LiDAR survey. And you can see the observed snow depth from that survey on the left here in 2009. And then for that same year, the simulated depth from the snow model up to that point. 0.88 correlation, which is pretty encouraging. We use this approach for all 4 years to get surface water inputs. That's snow melt and rain in each pixel at daily time set throughout the year. And the results showed that the snowdrifts in the basin were responsible for about 6 times more surface water input than the rest of the catchment. And importantly, the stream dryout was really correlated to the last day of melt in the snowdrifts. So I rushed through it, but data availability, you can contact me. Everyone's welcome to come to Reynolds Creek. We have some facilities for people to stay, but it's not too far away from Boise. It's a large city. Of course, all federally collected data is open access. And we welcome cross-site collaboration. We're part of the International Network of Alpine Research and Catchment Hydrology, or INARCH group. There's I believe about 40 or so watersheds internationally that we're sharing data with. Here's kind of a link to a 31-year data set that I'm currently updating to be a 40-year data set of all the variables you would need to run a snow model at 10-meter resolution. And then we are currently working with government IT personnel to kind of get our publicly accessible database back online. And importantly for that, we're currently taking applications for a database manager until November 6th. So I thought I'd plug that in. Unfortunately, it's for U.S. citizens only. So if you know anybody that's a U.S. citizen and is interested, have them reach out. And with that, I am done. Thank you.
Thanks, Andrew. Sorry, you kind of got pushed to the end here. But if there's anyone that's still on and has questions, we can do them for a few minutes. But if you have to go, understandable. Okay, great. Well, maybe no questions. I just will thank everyone for staying on a little bit longer than planned, and just let everyone know that I am wrapping up my role as the chair of the Sinter Executive Board. And so look for emails to come from someone else in the future. And yeah, thanks for everyone for coming, and nice to see you.
Thanks, Mackenzie. Bye.
Thank you.
Thank you for organizing. Bye.
Yeah. Thank you for presenting.
Yeah, thanks for the invitation.
Thank you.
It will be for you guys that did present. If you want to share it at all, it'll be posted on the Sinter website.
Yeah, sure. Sure, like if there's need, I can also share the presentation itself.
Okay. I don't know.
Oh, okay.
Simon is the one that does all the organizing things. So
Thanks. Bye.
Bye-bye.
Thank you. Bye-bye.